So our next speaker is Dr. Frank Loeffler from Jena. He has run the Einstein Toolkit for many years, although and he's done a lot of research in neutron stars. And so here he's going to give you an introductory talk on neutron stars. Frank?
Yes, so I hope that now works. Can you see something? Because,
yep.
Okay, good. So this talk will go into a bit different direction. So far, at least for today, we've heard about black holes, and that is really interesting, but it's not all there is out there. In some ways, this talk will also be a little bit different on the more technical side. This will be a really, really high-level talk. So all the senior people that I've seen in the audience here, they probably get bored because they know all that stuff. But if you are a student, you might be interested in some of that because it gives you a really high-level overview of how to do stuff. So in a very high level, this talk will have two parts. One is a short introduction on neutron stars and what that actually is. So if you know that already, you can just sleep for the next 10 minutes or not. There are some interesting tidbits as well in there, which can kind of motivate why we do this in the first place. And then I will talk about how, again, on a very high level, hydro is done within the Einstein Toolkit, which kind of thorns you need, which thorns interact in which way to actually make this happen. So let's start with that. What are neutron stars? So far we heard about black holes, which is essentially nothing. It's just vacuum. Yes, it's a bit more than just vacuum, but there's no matter. There's nothing more interesting than just vacuum there. So neutron stars are a special kind of star. And they're quite weird if you think about it, really. So their mass is not really weird. It's slightly above the solar mass. So they are a bit more massive than our sun. And if you think our sun is a quite ordinary star, or if you think about the sun being quite ordinary, neutron stars aren't that special from their mass point of view. However, you know that the sun is a lot bigger than Earth, but neutron stars with about the same mass, astrophysically speaking, they are only about 12 kilometers in diameter. I say 12, it might be plus minus 2 or whatever. That is not very well known, but I mean, just from this, you see that these are very, very dense. So the density you see there is about, again, astrophysically speaking, and about or above the density of the core of an atom. So not the density of atoms, but the core actually of atoms. So that's really dense. Essentially, you think about the star, compress it down to the size of the city you would be in if you wouldn't have COVID. So Baton Rouge, just compress that to about a size of a city, and then you have a really dense star. These stars, in addition, are rotating, or most of them are rotating, some of them really fast, and we will get to some of that. They are believed to have strong magnetic fields, and that means if you take all of that together, you get an environment that is unlike anything you can get on Earth. It's not anywhere close to anything you can get on Earth, which means you cannot experiment with matter in such an environment because you are not able to create that environment on Earth, not even close. You might think, well, you have colliders and everything, but you just don't have gravitational fields that strong. You don't have densities that high, and you cannot feasibly get that anywhere close or close to that on Earth. I don't know, the next 100 years probably, at least. But that means that the equation of state, so how that matter actually behaves in that environment, is not known very well. And very well, again, is astrophysically speaking. So some of the variables, well, is you might have a factor of 10 in there. So that is a field of physics where really it's not known what matter really does at that point. That it again means, well, you have these environments in these neutron stars. So that's one motivation why we actually look at these stars. if we find out something about those stars, we find out, or we hope to find out, how matter behaves in this environment, in, let's say, strong magnetic fields, but also in really deep gravitational wells. And so we might actually find something new about matter. So we can use those as laboratories if we want to. Some more trivia about neutron stars, just to show you how weird and how extreme these objects really are. So the gravitational constant, which kind of determines how strong gravity is about 10 to the 11 of that of Earth. So you would rate 100 billion times more on one of those stars. I mean, apart from the fact that you wouldn't survive it, that tells you something. The escape velocity is about a third the speed of light. If you can't get that far, you're stuck. If you have an object falling from 1 meter above the surface, that's still quite a bit. I mean, you have 12 kilometers of diameter, you have 1 meter above the surface. The time of that fall will be 1 microsecond. That's a really, really, really short time. And in that 1 meter, you will gain a velocity of 2,000 kilometers a second. That's your impact velocity on that neutron star. So that again shows you how extreme these stars are. I've told you that the escape velocity is 1/3 the speed of light. From this, you can also see, well, it's actually also influencing light around that star. So if you look at the neutron star, you actually see not just 50% or about 50% of the surface, but you see about 60%. Because part of the light that's actually coming from the back will reach you because the gravitational pull from the star is actually bending it to you. So that's what the picture here is kind of trying to depict. If you would see, you can see both poles if you have just the right orientation, for instance, of a neutron star. So that again is to show you how extreme these are, and that makes them really interesting, right? So how do these form? How do we actually get to that kind of star? Well, you have different types of supernovae that are most likely the prime candidate for actually getting these stars. That's mostly core collapse supernovae. There had been the idea of accretion onto a white dwarf, but that's probably not the engine for that. What you get if you look at these formations is that most neutron stars are initially really fast rotating. And if I say really fast, it's a few hundred times a second. Now, I already told you they have likely high magnetic fields. And we'll get to that. Just keep that in mind. They are rotating and they likely have high magnetic fields. The temperature, because of that type of formation, is initially really hot, 10 to the 11, 10 to the 12 Kelvin. But within a few years, it falls to maybe 10 to the 6 Kelvins or so. So they are initially quite fast cooling. I mean, fast because it's years, not hundreds or millions of years. And again, the behavior of matter, even during formation, is not very well known. Now, if you go a bit further and you say, well, at least after that time, what is the structure of one of those stars? Well, I've shown you here a picture, and that's a really cool picture and might not even be the most current one anymore. So what most models of the internal structure of neutron stars will tell you is that it likely has a crust, some kind of layers of nuclei, although it's really a really big nucleus, the whole star essentially. You might have some atmosphere above that crust, and nobody really knows what that is. It might be hydrogen, helium, carbon, different theories about that. It's not even known how high this atmosphere is. So theories there go to really micrometers to about a meter maybe. But the dynamics of the atmosphere, that's what most people at least agree on, is quite likely controlled by the magnetic field, because the magnetic field is supposed to be really. If you go a bit deeper than the crust, things get more and more uncertain. What most people assume is that's a superfluid, it's neutron degenerate matter. Maybe you have quarks in there. Nobody really knows what's inside one of those stars. So that's really a quite mysterious object still. It's really hard to figure out what it looks like.
Frank, your volume is cutting out a little bit. Just letting you know.
And make that a little louder if that's better now.
Yes, I think so.
Okay, good. Thank you. Thank you. Well, I told you they are rotating in the.
No, I take it back. We've lost you completely. Frank, I can't hear you at all.
Test.
Yeah, there you go.
There you go. I'm back again.
Yes.
Okay. Zoom isn't telling me anything. Okay, let's hope that works. Okay, so they are initially quite rapidly rotating. They do slow down.
Frank, we've lost you again.
That helps. Okay.
Yes.
Okay. Good. So once the rotation has dropped really, or has slowed down, you have a really low slowdown rate. This is on the order of 10 to the minus 15 seconds per rotation. So you get 1 second slowdown in, well, you get from 1 second to 1.03 seconds in 1 million years. That is used essentially when you use some of these as essentially clocks, because they essentially are very, very stable in terms of rotation after some times. What you do see is that you get glitches in this rotation. It's not quite clear why that is. So it's really, really stable, but at some point you get a glitch and it makes a short jump, and then it's stable again after for quite a while. So it might be starquakes or some reconfiguration of the crust, something like that. But then it's stable again. So that's the kind of reaction you get. But since you also have magnetic fields, if you have rotation and magnetic fields, and you have the poles not really, you have a misalignment between those two poles, so of the rotation and of the magnetic fields, you get radio emission, right? And that's where essentially you get pulsars from, and that's where you get a lot of information actually from. So most of what we know is actually from neutron stars that are pulsars, because you just can measure more stuff from them. One of the most rapidly rotating neutron stars rotates about 700 times a second. So that's kind of telling you how fast these things are. So just imagine 12-kilometer star, and then it rotates 700 times a second. Now, how many of these do you actually have? We don't quite exactly know. There's only a tiny fraction of neutron stars actually known. So there's supposed to be a lot out there, and we only know a few. Most of the ones we know are quite close to us, kind of obviously. So in the Milky Way, in the Magellanic Clouds, most of the ones we know are radio pulsars. That's because we can see them better. And most of them are in the disk of the galaxies, but you have a quite large spread there. One of the closest neutron stars is about 130 parsecs away, so that's about 400 light years. And also important for gravitational waves later on, about 5% of these neutron stars are within binary systems. So you do have neutron star binaries, or neutron star something else binaries. Now, what I wanted to show you isn't just still pictures. So
Unlike
let's look
with
at
some
that.
Hollywood films, a sequel of a movie from NASA's Chandra X-ray Observatory is better than the first. The star of this Chandra movie is the Vela pulsar, a neutron star that was formed when a massive star collapsed. The Vela pulsar is about 1,000 light-years from Earth, spans about 12 miles in diameter, and makes a complete rotation in 89 milliseconds, which is faster than a helicopter rotor. As the pulsar whips around, it spews out a jet of charged particles that race along the pulsar's rotation axis at about 70% the speed of light. The new Chandra data, which were obtained from June to September 2010, suggest that the jet may be slowly wobbling or
Frank, your audio is cut out.
Yeah, I think that's the video. So the video had a problem with the audio. So
Okay.
what you will see is, at the moment we are still zooming in, but what you will see is that they actually took several pictures of the same pulsar over, I think it was a period of a few months, and then they made a video out of that. And that's what you will see now. I hope that's visible. It didn't start yet. So that's one of the things I found interesting, because usually if you go to astronomy, you see still pictures, but sometimes you can actually see stuff moving. I don't quite know why this isn't playing anymore. I can link the original link to the video later on, so you can actually look at it. They're still doing something. I'm not quite sure why audio is gone now. So what you see in the middle is essentially, so in the very center, the really bright center, you have this pulsar, and you have some matter around it, which is just highlighted. But what you should see at some point when it starts moving is a jet, which the most visible part is to the top right. I hope that's not mirrored by zoom. And you will see essentially stuff coming out. So not just a still picture. I hope it carries over soon. So now you should see a bright spot in the center. You see some bright stuff around it. Still zooming for me. Okay. So now it should play. They only have a few images, so it would be a lot better. They would take it do that longer, but now it's hopefully visible that essentially you have this jet, likely to both sides, but the one you see better is the one to the top right, coming out of this pulsar. So you can actually see stuff going on in there. So now I go back to saying, well, I told you how interesting these objects are and how complicated and really extreme they are. And well, I guess most of you are physicists. So there you are probably familiar with the term of spherical cow. That's a cow. That's our neutron star, right? So what we can actually do, I guess, right now with the codes we have, with the computers we have, with the Einstein toolkit, for instance, is maybe something like that. It's not really a neutron star. Why is that? I will come to that. It's just because we cannot computationally do that at the moment. So if we do, let's say, a binary neutron star simulation, or just a neutron star simulation at the moment, these are really just rough numbers, right? Just to give you an idea. If you want to do general relativity, so you solve for the space-time evolution, and you want to do hydrodynamics, which is just the evolution of the matter itself, nothing else yet, you need some grids. So you need essentially mesh refinement to have a high resolution inside the star, and to be able to at the same time put the outer boundaries so far away that you don't have a strong influence from the boundaries. So you need a few mesh refinement levels and a grid that's above, that's about 100 or 200 cubed or something like that. So that at the end you get about 50 points across the stellar radius, and that's quite coarse still, but it's just one estimate, right? If you do that, you need about 50,000 core hours on a supercomputer for each model you run. Of course, those numbers change a bit. If you change resolution, they change quite a bit because it goes with the resolution cubed or even fourth. And it also depends on the model you run, but that's just to give you a few numbers. So you need some time, quite some computational time. You also need quite some memory to actually hold all those points in memory. So for those numbers, you need about a terabyte, and that's main memory, not disk, right? So you do need quite a few nodes to actually make up that memory. And then you need a few days on those cores. But again, that's that's just a rough estimate. What you also need is a lot of patience debugging your computer code, but that's something else. I will not talk about that today. Just to summarize neutron stars, that's just the first part of the talk, right? So they are very exotic objects and highly interesting. They do exist. For some time people didn't really know or didn't really believe they exist, but we actually quite certain now know they do exist. They are observed, and we still don't know a lot about them. One interesting fact, for instance, is that I already mentioned we don't really know the radius of a neutron star. But that would be really helpful to constrain the equation of state, but we just there's no good way to actually measure the radius of a neutron star. But what we do know is that whatever the radius is, the mountains, so to say, of a neutron star, they cannot be higher than a few millimeters at most. So it's kind of strange that we do know they are quite spherical, or let's say if they rotate, they are quite smooth, so to say. We do know that. And simulations of neutron stars, if you want to do them, they are quite expensive, but they are also necessary because there's no way to actually create those conditions on Earth or anywhere close. So that's the only way to actually learn something about them other than observing them, but that's really difficult.
Frank?
Yes?
I don't have a good way to signal you, but you should, your time slot should be up at 10:12, given our schedule slip or so.
That's fine, that's fine.
Okay, great.
So let's go back to gravitational wave physics, because that's a big part of what we do. I was talking about models. Well, actually, I started talking about observations. What we do is models, and then we want to analyze those, right? So if you look at the Einstein equations, how do we actually, what are those, right? If you look at the Einstein equation, they, at least in theoretical form, are in four-dimensional space-time. You have a gravitational tensor here and an energy momentum tensor there. I hope you see my cursor, by the way, I don't quite know. And then you can reformulate them for in three-dimensional space and with a time evolution, and you get all these equations that are listed here. So in particular, besides the space-time evolution, you get GRMHD hydrodynamics. So that means not just hydrodynamics, but also magnetic fields. And you probably have to deal with radiation transport. So you essentially face the problem of full numerical 3D models that you actually need, because those things wobble around. It's really hard to use symmetries there. Sometimes you can, but most often you cannot. And then if you want to have radiation, you get a lot more dimensions. So how do you do that in a code? Now let's look at the Einstein equations. That's a quite simple equation, but that's because all the complicated stuff is hidden in those symbols, right? But what are those? Well, G mu essentially deals with space-time curvature, right? Those are constants. They are easy. And this tensor here, the energy momentum tensor, hides all the complications about matter. And we have to write a code, and the Einstein tool is one of those, that actually deals with combining these two. Well, matter contains hydrodynamics, electromagnetism, particle radiation, whatever matter does. Might be even more than that. So let's look at that from the Einstein tool point of view. We have the space-time essentially described by a common base thorn, which is ADM base, which describes essentially a space-time in the ADM variables. We have one thorn that is called T mu nu base, which describes this energy momentum tensor in a really generic way, not assuming anything about the matter at all. If you have a space-time evolution, like for instance, this space-time evolution thorn here, McLachlan, then this will use ADM base because it's evolving the space-time. And it will need to know about the matter content, so it will also interface with T mu nu base. But it doesn't need to know anything more about T mu nu. It just needs to know T mu nu, nothing about the internal structure of that. On the other hand, if you have a hydro evolution, you have a hydro base, which just provides some variables that are common to a lot of the hydro evolutions. So that's the density, the pressure, temperature, quite a few others. And those actually go into T mu nu base. So T mu nu essentially calculates the energy momentum tensor from those variables, so I can do that. And ADM base is used for hydro base because in order to get from one to the other variables, you sometimes just need to have the curvature, for instance. Then if you want to have a matter evolution, you obviously need to interface with ADM base because the matter evolution happens in this curved space-time, so you need to know about the space-time. Then the matter evolution also provides T mu nu, or can provide that, and it will also populate those hydro-base variables. So that's essentially the interface you have on the example of McLachlan as a space-time evolution thorn and GR hydro as a matter evolution thorn. What you also need if you want to do a complete simulation later on is you need to have some initial data. So you need to have an initial data thorn providing both space-time and hydro. And because you want to analyze something, right, you need to have analysis thorns, which then again look at the variables in ADM base and in hydro base and potentially others, and just calculate whatever you are interested in. That also
1 minute warning.
Yeah, no problem. That also means you can have a lot of initial data thorns, analysis thorns. You can have a lot of space-time evolution thorns. You can have a lot of matter evolution thorns. You will hear about some of them within this workshop. So what you already did is kind of that. It's not really a cow anymore. It's a sphere. It's a really, really, really simple model of a neutron star. That's the smallest example we can probably come up with, at least using the Einstein toolkit. That's what you already did. You already ran one of those. You've already simulated a neutron star. But a big warning there, it's a path file optimized for speed and low memory. Don't do physics with that. You can't. If you want to have a bit better example, go to the gallery on the website. There you will find a path file for a single neutron star. It's a little larger. It's still a toy. I've given the URL here. You will get, let's say, a density evolution looking like that. You also find there a binary neutron star parameter file. And with source code provided, you can just run that on your own system. You can evolve a binary. It's a bit more computationally expensive. If you want to get a bit more than just this here, and that's my last slides really, then you can, for instance, go to some publications that actually include all the parameter files, all the source code you need. You can essentially repeat all of that. For instance, that actually works. Something like that, a binary neutron star simulation, and you get essentially in the end to movies like that. You get two neutron stars merging. They are really heavy, but only after some time a black hole forms and you get some matter spinning around, and I'm cutting this short now, you get a torus of, in this case, very low density matter. So that is actually something you can do with the Einstein toolkit, or at least with big parts of it, and the rest is public as well. And my last example here is you can actually simulate some of the not just hypothetical binaries, but you can look at some of the binaries we actually see and observe, and you can actually input those numbers like the mass ratios and the orbital velocities and all that kind of stuff. You can actually simulate those, and you can you have all the parameter files and source for that. So now the question is really only which results will you have for the next, let's say, 10 years. It's 10. So in 2020 something, in order to get to that cow, because in the end we want to know what neutron stars look like and not what our simplified models look like and do. But that's essentially something we can leave up to us or up to you. And that's my last slide.
All right. Thanks, Frank. Virtual clapping. We have a question for you. Are there any cohesive resources for learning to generate initial data for neutron star simulations? I've tried using Lorraine for initial data generation, but the documentation wasn't very new user friendly.
That is so true. I can feel you. Yes. I don't think there's a tutorial or something on it. There are examples. I mean, the examples I mentioned in the last two slides, essentially, they both use Lorraine to, even the second example I've shown you, use Lorraine. But of course, in those examples, you essentially get the input files for Lorraine, but you don't get a large documentation of what those things actually mean. So I'm not aware of a good tutorial on that. I know Lorraine is a bit hard to understand at times. So sorry, I don't know about good tutorial about that. So essentially talk to someone who actually used it in the past. That's probably the best shot.
Does GR Hydro account for the electromagnetic part as well?
Well, GR Hydro contains evolution for that. Those examples I've shown here don't use that though. So you can do magnetic field evolutions with GR Hydro, but that's not in the examples I've shown here.
Okay. Thank you, Frank, for your talk. I think that's all the time we have for questions.